Hello, this is Expanding Logarithms, and we are looking at this side of the expand condensed logarithms today. And so I've included the rules that apply to both expanding and condensing logarithms, that are the operations with logarithms, which you can see right there with 1, 2, and 3. There's also this fourth rule, which is the change of base formula, which may or may not come up in our practice. We'll see. But with the operations with logarithms, you can see the similarities between the exponential rule, which I've got written right here. If you multiply two variables, then you add their exponents together, and those variables have to be the same variable, or in this case the same base, in order for you to add their exponents. And you can see that with that similarity and that symmetry between these three rules. So if you multiply inside the argument of a logarithm, then you're going to add the two separate logarithms with those arguments split together. And then so that's the multiplication rule, and then we've got a quotient rule where we subtract the numerator and denominator in the quotient of a single logarithm, and then we've got the exponent rule where we take the power on the base inside the argument and we multiply that to the entire logarithm. So that's like the power to a power rule for logarithms. So we're going to use that. And I've also added a few more rules here, just in case you've forgotten these. These are other properties of logarithms and exponents. So if we have a logarithm with the same base as the argument, then that's like saying, what's the exponent that has that makes a base a with a that makes a with base a. So that would be 1. And then this second one over here is asking for what is the exponent, because remember, logarithms are exponents. What's the exponent that has a base a and it equals 1? So how do you get 1 out of a base a? Or if you want me to write this like so, it would be like a to the power of what equals 1. So that x is going to be 0. And then these are our inverse properties over here. So if we raise a to the power of log base a, then that's going to be the argument. And then if we have inside our argument of the logarithm an a to the x with the base being a in that logarithm, then x is going to be the output. So these rules are important to keep in mind as we traverse these next examples. So 17 through 22, yes, I know they can be solved just by converting them to the exponential form, but we're going to go through expanding these logarithms with these rules. So I'll leave that up there, and we'll tackle 17 and 18 and 21 and 22 with those rules. So first thing we're going to do is take 8, and we're going to make it 4 times 2. And from there, I can expand multiplication inside the argument to addition between the logarithms. So we're just practicing with these rules. And so that makes sense. Everything we've done is valid. And then I need to start simplifying some of these things, because the point is to evaluate, so we want to figure out what this expression means. So log base 4 of 4, we know what that is, because that's the first one here. It's going to be 1. And then plus log base 4 of 2. So this log base 4 of 2, we're actually going to write 2 as if it had a base of 4. And we'll get into later why we're going to do that. But for right now, we know that 2 is also 4 to the 1/2. So I'm going to keep on expanding this. So I've got 1 plus log, and again, this is the long way of solving this problem, but I'm just showing how you can expand this to solve it. So I'm going to have 1/2 out in front, because this is 4 to the 1/2 inside my argument. So I'm going to use my power rule for logarithms, which means I'm going to put that b out front. So I'm going to put the 1/2 out in front of the logarithm. And what you have to understand about these logarithms is when I have parentheses here, that does not mean multiply. That is the 4 inside the argument of the logarithm. But out here, out in front of the logarithm, that does mean multiply. So now I have another rule like this, where I've got a log of 4 to the with the argument of 4. So that's going to be 1 as well. So I've got 1 plus 1/2. That equals 3/2. All right, so here we're going to tackle 18, and at first, if we were going to multiply log base 2 of whatever 4 squared times 3 to the 4th is, so 16 times 81, we would have 1296. And we don't know what exponent gives us that argument. So we're going to instead split this into log base 2 of 16 plus log base 2 of 81. And now it should be apparent why we can't find a good exponent for this. We can't find, so we can't say 2 to the x is equal to 81 for this side. We can't find anything that good. So if we're leaving this in logarithmic form just to evaluate, then log base 2 of 81 is exact as we can get it. So if we would just have to use a calculator to figure out what that is. But over here, we know what power gives us a 16. So log base 2 of 16 is going to be 4. So we have 4 plus log base 2 of 81. So again, purely just practice, we're just using this to expand. Now, for 21, we have natural log that can be split up using the sum property, or the multiplication property. And now we see the power on logarithms, or in the argument, being used, or becoming multiplication on a logarithm. So 6 natural log of e is what this becomes. And now that we have this simplified, we know we can't evaluate this because we can't find an exponent that gives us a nice number for that. So we're just going to leave that left side as natural log 5. And then this natural log of e, well, natural log and e undo each other. And remember, this is log base e with a e as the argument. So this is essentially 1 because of this first property here that I mentioned. So this is 1 times 6, so it's just 6. Yay, so we got that simplified. Now 22 is going to actually use the quotient property. So we've got natural log of 6 minus, so everything that's under the division bar in the denominator is subtracted in this logarithm minus natural log of e to the second power, and then we can keep on simplifying this. So we'll still have a natural log 6 left over because we can't simplify that, minus 2, and then natural log of e, and we all know that that is going to undo each other, so that just becomes 1, so natural log 6 minus 2 is what we have left over, and that's as best as we can get it. And now we're going to expand with variables. So on 48, we're going to just split things up, even the coefficients and the variables. So our logarithm, and we can do everything in one step if we feel more comfortable, will be log with argument 4 plus 2 log x plus log y. And I kept everything with the same logarithm and just used that multiplication property that turns it into the sum of logarithms. Now 50 has division in it and it has some powers on its variables, but what I see as well is I can factor that numerator. So I'm going to go ahead and split this up into, and I'll factor as well. So I'll have x minus 1, x plus 1, because it's a difference of squares, in my numerator, and I'll subtract my denominator as a logarithm. So x cubed. And then now I can keep on expanding this now that I've factored. So natural log of x minus 1 plus natural log x plus 1, and then minus 3 natural log x because of that power. Lastly, this natural log, remember that cube root is the same thing as a 1/3 power. That's really important. And not only that, but that 1/3 power is on both the numerator and the denominator. So this 1/3 power applies to the x and to the y. So in order to start this thing off correctly, I need to have a 1/3 and then my natural log of x minus natural log y. And so I need to either put parentheses there or also show that this 1/3 is distributed to each the natural log x and the natural log y, because that 1/3 and that cube root definitely applies to the x divided by y. So be careful of that. This whole thing is just a lesson in how good are you at grouping and seeing groups within other types of groups. So again, we had some academic practice with 17, 18, 21, and 22, but I hope everything came back together for you with 48 through 53. Thanks for watching, and I'll see you later. Hey, I'm back. This is solving using the one-to-one property. The one-to-one property is useful because it helps us solve complicated equations easily. So we can solve certain exponential and logarithmic equations if either side of the equation has the same base. And that's really important because what that allows us to do is we can set the arguments or the exponents in either case equal to each other. And basically it just becomes this algebra 1, algebra 2 problem. And it's really important with logarithms, and I'll point this out later, that each side of the equation must have a single logarithm. If it has multiple logarithms, then you're not going to be able to use the one-to-one property. So starting off with this exponential side of things, we want 8 to have the same base as 2. So we can use the one-to-one property. So 8 is 2 cubed, and this is where it's really important that you've got this knowledge about powers. What's 3 to the 4th? What's 3 to the 5th? What's 2 to the 6th, for example? Those are the types of things that you'd want to have ready to go. You can think about it. If you can think about it pretty quickly, then normally you'll be all right. You might have to do a little bit of figuring, but that's what's going to really make these easy for you. So we know that 2 cubed is 8, and now we can use the one-to-one property because we've got the same base, 2 and 2, on either side of the equation, and we can set their exponents equal to each other. So this is x plus 1 equals 3, and we know that x equals 2. Yay! Number 3 has 5 and 125. Now, it's great that we've got a prime base, so we don't have to do anything to this base, but we do have to manipulate 125 so it looks like 5 to the power of something. So this is 5 cubed and 5 to the 1/2 x plus 4. And now that we've got this relationship, 1/2 x plus 4 is equal to 3, and -1 is equal to 1/2 x, so x equals -2. Great. For number 4, we have a little bit of a strange situation on this one because I see the same base, 3 and 3, but that right 3 is in the denominator. So how do we make this look like, because we prefer, if we want to be really technical about it, we prefer to have a to the x equals a to the y. We don't like to have a to the x equals 1 over a to the y. That doesn't really help us out. We can't set, in this case, we actually can't use the one-to-one property. We can't set x equal to y just yet. So if we want a to the x equals a to the y, then we need to move this 3 to the numerator. So we need 3 to the -1, because that's what 3 looks like if it were in the denominator, but represented with an exponent, making it in the numerator. So I've got 4x minus 1 equals -1, and I'm going to have x equals 0, because I add 1 to this side, and yeah, there you have it. With 7, now we have a little bit of a tricky one, because 4 and 32, I can't think of a power. I can't raise 4 to, I can't square it, I can't cube it to get 32. So we sort of have a problem there, but we can find a common base between 4 and 32. So 2 to the 5x minus 1, I should really have 2 times 2 to the 5x minus 1, 2 to the 2, with that 2 in the exponent times 5x minus 1, is going to equal, let's see, what is 32 if we're raising it to the power of 2? 32 is equal to 2 to the 5th. So if I've got the cube root of 2 to the 5th under that radical, then this is actually 2 to the 2 times 5x minus 1 equal to 2 to the 5/3, because this cube root is a 1/3 power, and now I can set 2 times 5x minus 1 equal to 5/3. So this is 10x minus 2 equals 5/3. And then I can start operating and solving. So 10x equals, if I add 2 to this side, this is going to be 1/3. Oh, what am I thinking? 11/3. And then I need to divide each side by 10. So I've got x equals 11/30. I just multiply each side by 1/10. Yeah. Great. Now, lastly, these two are pretty strong. The idea on logarithms, and I mean they look strong. The idea with this logarithm for 54 is that we can have the same base. We can have the same base on each of these, and just go about setting the arguments equal to each other. But we can't, because this last thing, this is 2. So how do we make 2 look like it has a base, as a logarithm of 6? So to remember that, we've got to go back to this rule where log base a of a is equal to 1. So there is a 1 hidden in here. So I'm going to change this to 2 times log base 6 of 6. And that means what I actually have in my argument here is log base 6 of 6 squared. So now that I've got I've just used my condensing rules actually of those operations on logarithms, I can set the arguments. So here's my new argument, 6 squared equal to x and 3x plus 6. So I've got, 35x plus 6. So 35x plus 6. Oh my gosh, I jumped the gun. I almost forgot. We almost forgot the rule we had here. We have to have a single logarithm on one side. So, glad I caught that. So we actually need to have 35x plus 6 divided by x on one side equals log base 6 of 6 squared. Now I can set 35x plus 6 over x equal to 6 squared. Great. This is much better. So 36x is going to equal 35x plus 6. And if I subtract 35x from this side, then I'm going to have x. Yay. So that one started off a little tricky, but really the one-to-one property is pretty easy for that, and applying that. So with this last one, we don't even have to worry about one of these items, one of these terms, not having a common base. They're all natural logs, so they all have base e. So that means all I need to do in order to finish this one is multiply 2x minus 3 and x plus 4. So 2x minus 3 and x plus 4 are in a logarithm together, and they equal this other logarithm on the right side of the equation. So now that I've established this, I can set my arguments equal to each other. So what I'm going to do is multiply this 2x minus 3 times x plus 4 and combine like terms, and then I'm just off with an algebra problem. So I've got 2x squared plus, let's see, that's 8, so 5x, and then minus 12 equals 2x squared plus 15. And it looks like I can cancel out some things here, so my 2x squared goes away. My 5x is equal to 27. So x is equal to 27 divided by 5. Woo! And there you have it. So that is how you evaluate using the one-to-one property. And thanks for watching. See ya.